Hello guys, welcome to my video. So then we'll be solving the May-June 2023 paper 2-2 for physics, and the paper is 1 hour 15 minutes long. So I'm going to be explaining some of the concepts and how you can answer some of the questions. So please comment, like and share if you really like the content so that it can help me create more videos, okay? So here are some of the data formula that you'll be expected to know. And some of the formulas, for example, the Doppler effect, resistors in series, resistors in parallel. Okay, so let's begin. So the first question is define pressure. Okay, so this is a definition question, and pressure is just the force per unit area. Okay, but that area must be normal to the force. Okay, so if you have a certain area and you apply a certain force on that area itself, that is what we call pressure, okay? You might have a certain area that you have, and you apply a certain force F to that area A. We say you're exerting a certain pressure on that area, okay? Moving on to question number 2. Moving on to the next question, we've been asked to use our answer to show that the SI base units for pressure are actually kgm to the power of -1 s to the power of -2. So what we're going to do is we know that pressure is equals to force over area, okay? So the units of pressure, we'll put that in brackets, will be equivalent to the units of force divided by the units of area, right? But what are the units of force? We know that the units of force is measured in newtons, but generally the units of force, okay, are generally kgm squared s to the power of -2. Why is this? Well, because we know that Moving on to the next question, we've been asked to show that the base units of pressure are kgm to the power of -1 s to the power of -2. Okay, so the units of pressure, okay, will be equal to the units of force, because we say that pressure is the force per unit area. So the unit of force, okay, divided by the unit of area, right? But we first need to know what is the unit of force, okay? So the unit of force is actually kgm s to the power of -2. Now we know that force is basically just measured in newtons, because it's the mass multiplied by the acceleration. The mass is measured in kgs, and the acceleration is measured by meters s to the power of -2. And the units of area, okay, and the units of area are basically m squared. So if we divide these two, so kg ms to the power of -2 divided by m to the power of 2, that gives me kg m to the power of -1 s to the power of -2. So basically, whenever a question asks you to show, they really want you to show all the concise steps so that they can be able to see if you really understand how these things work, okay? Moving on to the next question, we've been given a horizontal pipe that is a certain length L, okay, and a circular cross-sectional area of radius r. Very important for you to know what the question is saying. And you've been given mass m of liquid that flows through the pipe in a given time t, okay? So we've been given that mass m, and we've been given that formula, and we've given P1 and P2 as the pressures at the ends of the pipe, and K is a constant. So we've been asked to determine the SI base units of K. How do you go on about this? Well, the best way that you can do is you make K the subunit of formula. That makes everything so much easier. So it's M8KL is equivalent to pi P2 minus P1. We'll close that. R to the power of 4, the density multiplied by T, okay? So that means K, we leave K on that side, will be equivalent to pi, okay? P2 minus P1, R to the power of 4 multiplied by density by time divided by M8L, okay? So that is the value of K, because they've asked us to determine the SI base units of K. So what do we know? What are the units of R, and what are the units of rho, and what are the units of T and the units of L? So basically the units of K, okay, so the units of K will be equivalent to the units of, so we can just put square brackets, sort of represent those units of P2 minus P1, R to the power of 4 rho times t divided by the units of m and l. Okay, so these coefficients don't matter. For example, pi and 8, right? They're just coefficients. They are numbers without any units. So in order to make this easier, what you can do is then just list everything that you know, and that will make it so much easier for you to understand what the units are going to be. For example, the units of k, okay, so let's start. The units of r, we know that r is the radius, right? But r to the power 4 will be m to the power 4, because that's the units of radius, right? The units of our density. Density is actually mass per unit volume. Mass is measured in kg, and volume is measured in m to the power of -3. So the unit of density will be kg m to the power of -3. The unit of P2 minus P1. Okay, so the previous question, physics questions usually relate to each other. The previous question had asked us to calculate to show that the SI base units of pressure are that. And this question has told us that the final pressure, P2, minus the initial pressure, P1, is given by that expression. This will have that same units, okay? This will have that same unit. So it will just be kg m to the power of -1, s to the power of -2. Well, why is that? Well, imagine you're saying 5 kgs minus 4 kgs. The answer that you have will just be in kgs, just 2 kgs, right? So it doesn't matter whether you're adding or subtracting quantities. That doesn't change the units, because the answer that you get will just have that same units, okay? And the units of m, we've been told that is the mass is in kg, and the units of L, which is the length, is also in meters, right? So we have all of these quantities that we have, and now we just go in and we feed our values, and we'll get our units of K. Okay, so the units of K will be equivalent to, we have this value of pi that we over here. We ignore that. So we'll first start with pressure 2 minus pressure 1, which is kg m to the power of -1, s to the power of -2. Then we multiply that by r to the power of 4, which is basically m to the power of 4. Okay, so that's basically m to the power of 4 multiplied by density, which is kg m to the power of -3 multiplied by time, which is s, divided by ml, which is just kg, okay, and m, which is for the length. Okay, so basically these are all the units that we have, and we can then find the units of k, right? So these kgs cancel out. So our whole goal is for us to find what the units of k will be. Okay, so we also have again a kg over here, which is left. Okay, so this m, right? So let's simplify it. So it will be m to the power of -1 plus 4 minus 3 minus 1, which is here at the bottom. Okay, and s to the power of -2 multiplied by s, right? We still have our kg over there. That gives us kg. Okay, so it's plus 4 minus 3. That actually gives us plus 1 minus 1 plus 1. That gives us -1, right? So it's -1 plus 1, 0. We're left with that -1. So m to the power of -1, and s minus 2 plus 1 gives us -1, right? So this becomes our units of k, which is kg m to the power of -1, s to the power of -1. Okay, so remember this, right? Just first write the equation that you have. That's why it is 3 marks, right? You first need to know certain quantities. So I just advise you just list them down nicely, and you'll be able to identify the units of the quantities that you're required to know. Moving on to the next question, we've given an experiment that is performed to determine the value of k by measuring values of other quantities in the equation. The values of L and R have a percentage uncertainty of 2%, right? State and explain quantitatively which of these two quantities contribute more to the percentage uncertainty in the value of k, right? So it's very important for you to understand what exactly goes on, right, whenever we have percentage uncertainties, right? So if you have an equation, let's say you want to find the value of k in here, right? You say the percentage uncertainty in this density, right? And then you find the percentage uncertainty in R, in density, in that pressure, in time, in mass, and it's in length, right? So you'll be finding those percentage uncertainties, and you'll be multiplying by their powers so that you can be able to get the answer that you want, right? So it's very important for you to be keeping that in mind, so that you can be able to get the answer that you want. But remember that whenever we raise something to a power, for example, r to the power of 4, that will actually be 4 times the uncertainty that we have to R, because we have 4 errors that have each a percentage uncertainty of 2%. So they contribute 4 times that percentage uncertainty. So the answer is R contributes more, right? So R will definitely contributes more. Okay, so R contributes more because it is multiplied by 4, right? Because its uncertainty is multiplied by 4, right? By 4. So that's actually 4 times 2%, which is actually 8%, right? So R contributes 8% and L just contributes, right? And L contributes 2%, right? So L will just contribute 2%, but R will contribute 4 times 2%. Hence, R will contribute more because its uncertainty is multiplied by 4. So very important for you to remember this, right? There are 2 aspects to this question. They said I've stated that R contributes more, and I've explained by saying that it contributes 4 times more than the other one. Okay, moving on. We've been asked what is meant by the center of gravity of an object. So what is the center of gravity, right? So this is basically a point where all the weight of an object is taken to act, right? So it's a point where all the weight of an object is taken, right, to be acting. So it's a specific point, okay? So it's a specific point on a particular object, right? Where all the weight is taken to be acting, right? Or it's assumed, right? So we can say taken, we can say assumed, right? So we assume that all the weight is concentrated at that point. You'd realize if you're trying to balance a ruler, you'll be trying to find a certain point where if you align with that point, the ruler will be balanced. What you're doing basically, you're just trying to find the center of mass. This is a point where all the weight of an object is assumed to be acting. And once you find that point, it'll be very easy for you to balance that whole thing. So basically, that is what you need to know about the center of gravity. Move on to question number B. We've been given 2 blocks, okay? So we've been given this block and that block. They have different weights, as you can see here, 54 and 2.4, right? So a large block of 54 is at a distance of 0.45 from the pivot. That small block is at a distance of 2.4, a distance of 0.95 from the pivot, and a distance from 0.35 from the right hand of the beam. So we've been given these 2 distances. We just need to know which one of these is true. By taking moments about the pivot, calculate the tension in the string. What is moment? Well, a moment is basically the force multiplied by the perpendicular distance, right, from the line of action of the force to the pivot. That is basically what a moment is, right? If you have opened a door, for example, you pull the lever down, you exert a force, right? That force causes the door to rotate down, right? A turning effect arises because of what you're doing to the door. That is basically what a moment is, a turning effect that arises due to a force that is perpendicular to the line of action of its action, the line of its action to the pivot itself, right? So the principle of moments would then state that if an object is in equilibrium, as the question tells us, that this object specifically is in equilibrium, it means that the anti-clockwise moments will be equal to the clockwise moments, right? So let's go. The summation of the clockwise moments, right, will be equivalent to the summation of the anti-clockwise moments, right? So we just need to find the clockwise moment. And this is the normal clockwise direction that you know, like a watch, right? Clockwise, you're going in that direction, and anti-clockwise, you're going in the other direction, right? So let's see. Let's see which forces are acting in the clockwise direction. So we have this 2.4. Remember, it's the distance from the pivot itself, right? So the clockwise moment, the first one is 2.4 multiplied by our distance, which is 0.95, okay? 0.95 plus, do we have another clockwise moment force? Or we have this tension. If we resolve it, if you remember resolving vectors, if we were to resolve this into this component that will be acting down, this component is actually t sine of 30, right? So it will be that plus t sine of 30. But what is the distance, guys? So if we were to add these 2 values, 0.95 and 0.35, the total will be 1.3. So plus 1.3, right? So these are the only clockwise moments. So they're causing this object to try and have a turning effect in the clockwise direction. But the weight here that is bigger is trying to do the exact opposite. It just wants to turn the beam to the right, to the anti-clockwise, right? So these forces on this other side wants to push it down. Those other forces want to push it anti-clockwise, right? So these two have to be equal. Otherwise, this whole thing is going to fall down, right? So this will be equivalent to 54 multiplied by, but what is the distance? So let's see. The distance from the pivot is actually this distance, which is 0.45. So multiply by 0.45. And our goal is for us to find the value of our tension, right? So basically our tension will therefore be equivalent to, okay, so our tension will basically be equivalent to 54 times 0.45, right? Subtract 2.4 times 0.95, right? And we divide by sine of 30 times 1.3, right? But I would advise that you break these calculations down. First, calculate 54 times 0.45 separately, and calculate sine 30 times 1.3 separately, and then just divide it after you've separated it. Don't just go around and just put all the values out, because you might make a mistake in getting the value of your tension. If you compute this, you get a value of 34 newtons, right? So that is the value of our tension. The string is cut, okay, so that the beam is no longer in equilibrium, right? Calculate the magnitude of the resultant moment about the pivot, right? That is acting on the beam immediately after the string is cut, right? So what is happening? We have cut the string, meaning that we no longer have the tension that is present, right? And because we have lost that tension, meaning that there's going to be a resultant moment, right? So we can look at it in this way, right? We can say that the clockwise moment is actually positive and the anti-clockwise moment is actually negative, right? So let's go and see what moments do we have, so that we can be able to find how we can be able to solve this problem, right? So as you can see here, right, with 54 newtons and 0.45 that will be acting downwards, right? Okay. Right, move on to question number 2. The string is cut so that the beam is no longer in equilibrium, right? So if you go here, we are cutting the string and we no longer have that tension, right? So since that tension was helping the clockwise moment, if that tension is gone, the 2.4 will be feeling the pressure on its own, right? So this thing is not going to be stable, right? It's going to be falling to a certain direction, and we just want to find that resultant moment, right? So I'm going to assume that in that clockwise direction it's positive, and in that anti-clockwise direction is negative, right? So it's just convention, anything that I just want, so that I can be able to calculate that answer, right? So my anti-clockwise moments would be how many forces drive on the anti-clockwise? It's 54 times 0.45, okay? So 54 times 0.45, right? And then we subtract, right? Since the other one is going to be in negative direction, right? That would be 2.4 times 0.95, right? So 2.4 times 0.95, and that gives me a total of 22 Newton meters, right? So because I've actually removed that force, right? I've removed the tension that was acting, the resultant moment is going to be in this direction, and this whole thing is going to topple over and it's going to fall. But it's going to have a resultant moment of 22, right? The clockwise will be trying its best to sort of stabilize that, because if it wasn't doing that, we're supposed to have 54 times 0.45 only. But that 2.4 is doing its part so that it can stabilize things. So it just fall to the other side with 22 Newton meters, okay? Move on to question number C. So it's still that same question that is carried on. Now we're looking at projectile motion, right? So we've been given that beam as it rotates when the string is cut, the small block of 2.4, right? So this is our small block. This block is sort of projected in the air, right? So it's sort of thrown in the air, right? And Fig 2.2 is now showing me the last part of the path before it's about to reach the ground at point Y, right? So at point X, on that path, it is a speed of 3.4 and is at a height of 1.8, right? And we've been asked to calculate the decrease in the gravitational potential energy for its movement from X to Y, right? So how do you find the decrease in gravitational potential energy? Remember, the first mark that you get in physics, they'll just want to know if you know the formula itself, right? So the delta in GPE will actually be mg delta H, right? You, for just stating this definition, you get a C1 mark, right? Because you know what the formula is, right? So if you just know that, okay, gravitational potential energy is calculated in this way, but if you don't tell us the formula, you won't be able to get your mark, right? So you need to be able to state the formula first. We know that mg is actually the weight, which is 2.4, because this has a weight of 2.4 newtons, right? So this would be 2.4 multiplied by, but what is the change in height? Well, it was once at a height of 1.8, but it reaches the ground when the height is now 0, right? So that decrease will be 2.4 times 1.8, and that gives us a total of 4.3 joules, right? So the decrease in gravitational potential energy will be 4.3 joules, right? So you get your mark for your answer, right? This answer that you have given out, and then you get your mark for that particular itself, for that decrease in gravitational potential energy, right? So those are the 2 marks that you'll be getting from this question. Using your answer to Ci and the conservation of energy, determine this kinetic energy of the block at Y, right? So we want to find the kinetic energy of the block at Y itself, right? So let's see. We've been told that the block at point X, right, it has a speed of 3.4 meters per second squared, right? And it's at a height of 1.4, 1.8 above the horizontal ground, right? There's something that is different about this question itself, right? How can we find the kinetic energy that is present at Y? Well, we have to look at the energy that is present at X. Conservation of energy means that I don't lose energy and I don't gain energy whatsoever. So at point X, I have this amount of kinetic energy, but also I have a certain amount of gravitational potential energy. So both of that combined, the gravitational energy will keep on decreasing until everything just becomes kinetic energy. But at point X, right, I have both kinetic energy and the gravitational potential energy. But at point X, I only have kinetic energy. Where did that energy go? All the gravitational potential energy was converted into kinetic energy, right? So if I'm going here using my law, so kinetic energy, okay, kinetic energy at Y will be equivalent to kinetic energy at X, right? So the kinetic energy at X, but we must add the gravitational potential energy, right, at X as well, right? So we have 2 energies that are present at X, and they must be equal to the energy that is present at Y. So how do you go about this? Well, the gravitational potential energy therefore will be quite easier, because at X we know that it's half mv squared plus mg delta H, right? So that is the kinetic energy at X. And mind you guys, we have 3 marks here, and that is the answer that we're trying to find, right? The first mark comes from you just knowing that formula, that half mv squared is actually the formula to find kinetic energy. So again, you might know this stuff, but if you don't put that formula down, if you just go in and start writing down without telling them that that is the formula for kinetic energy, you won't get that mark, right? So if we were to go here, we have half, right? What is the mass of that block? It was actually 2.4, which is our weight, divided by 9.81, right? We know that weight is equals to mg, so mass will be weight divided by the gravitational acceleration, right? What is the speed? It's actually 3.4 squared plus, in the previous answer, we've calculated our gravitational potential energy to be 4.3, right? So if we were to calculate that kinetic energy, that gives us an answer of 1.4 plus an answer of 4.3, and in total that gives us a total of 5.7, right? So that's 5.7 joule kinetic energy, which is the amount of energy that we have for the block as it is reaching point Y, right? So all the gravitational potential energy has been converted into kinetic energy. So the kinetic energy at Y is actually greater than the kinetic energy at X. The next question, state the variation, if any, in the direction of the acceleration of the block as it moves from X to Y. Does the acceleration change as we move from X to Y? Well, no, right? There is no change to the acceleration, right? So there is no variation whatsoever, right? So no variation. And the acceleration remains vertically downwards, right? And acceleration remains vertically downwards, right? vertically downwards. Well, what do I mean by this? I mean, the acceleration doesn't really change that much, right? It just remains down and it remains acting in that direction itself. It doesn't change and start acting in another direction. The weight causes acceleration downwards, and that is always going to remain constant at 9.81. So acceleration will never change as the block moves from X to Y, but provided that there is no air resistance, right? Air resistance is negligible. That means that the magnitude of the acceleration will never change. Moving on to question IV. The block passes point X and its time XY, right? So we've been asked to sketch a graph showing the magnitude of the horizontal component of the velocity, right? So we've been asked to draw a graph that shows the magnitude of this horizontal component. So I need to advise you on these questions, right? They've been coming a lot. They're usually worth 2 marks or 1 mark, and they ask you to just draw graphs, right? So there are 2 things that are very important for you to understand, right? The first thing, there could be equations, right? What equations do you know? They could be things that can help you to figure out the shape of this graph. For example, if it's a y is equals to x squared graph, the graph would actually look like that, right? Provided that the relationship actually proves that y and x are related in that relationship, right? For example, if it's actually y is equals to the square root of x, right? So y is equivalent to the square root of x. If it gives that certain relationship, it actually means your graph will be something like that, because that is the relationship of a square root graph, right? If it's just y is equals to x, right? For example, if it's just y is equals to x, your graph will just be a straight line. So you have to be very careful as to what exactly does your graph want you to do? What exactly is your graph requiring you to do? Because that comes in a lot of questions and you need to be able to answer that. But in this question, we don't really need to use equations. We just need to use a bit of understanding of what happens to the horizontal component of velocity, right? It doesn't change. The velocity that an object will be moving at as you move from X to Y doesn't really change. So it just remain vertical as the object will be moving from X to Y, right? So there won't be any variation to the horizontal component of the velocity because there's no force acting in that direction itself, right? So you just need a horizontal straight line that you draw, but it's at a non-zero value of that velocity. If it was 2.5, it would just remain at 2.5. Moving on to the next question. We'll be given a block, so this is mainly dynamics, right? So we're answering a kinematics question. Now this is a dynamics question, right? So we're given a block that is pulled by a force X in that direction, and it's encountering a total resistive force in that direction, right? So the first question asks is requiring us to define the force, right? So these are the kind of questions that you must get correct. They require certain terms that you need to give in these equations, right? Or in these definitions, right? So force is actually the rate, right? So force is the rate of change of momentum, right? So basically, that is what force is, right? And just by stating this, you get your B1 mark, right? So because you know what force is and you know what it means, you can be able to get that mark, right? So we've been asked to determine the change in momentum from time t is equals to 0 and time to time t is equals to 3.0, right? So whenever you see a graph, it's a high order question. You have to study the graph very carefully. There's some information that they want you to know, and there's information that they want you to tell, right? So if we go back to our graph, we're given a force X that is being applied, right? And we've been asked from time t is equals to 0 to time t is equals to 3. And we want to determine the change in the momentum of the block itself, right? So basically, we know that the resultant force from what we have defined here, we've said that the force is actually equivalent to the change in momentum, right, divided by time. Okay, that is basically what a force is, right? What is the change in momentum, and we divide it by a certain time that is actually occurred. But what is the resultant force, right? This isn't just any force. If we look at this graph, the value of this force of X, right? So if we were to read our graph very carefully, it's 1.0 here, 1.1, 1.2, 1.3. This is actually 1.4, right? So this force X that is going on is actually 1.4 newtons, right? But remember this, it's encountering a resistive force of 0.8 newtons. So whenever we talk of the change of momentum, we're actually referring to the resultant force itself, right? So the change in momentum will be equal to the product of the force multiplied by the time. But that force, remember, is the resultant force. So 1.4 subtract 0.80 multiplied by the time, which is actually 3 seconds, will give you a change of 1.8, right? So the change will be 1.8. So your first mark is, do you know this formula itself, right? So if you know this formula and you get your answer correct, you'll be able to answer this question, right? So remember, whenever we say force is equals to the rate of change of momentum, whenever we change momentum, it's because of the resultant force. Go back to your question. What force am I applying? Is there any force opposing me? Therefore, the resultant force will be the difference of those two forces. Okay? I'll move on to the next question. We've been asked to describe and explain the motion of the block between time t is equals to 3.0, okay, and time t is equals to 6.0. Remember, like I always say, whenever you see a graph, it's a very high order question. Try to analyze and understand what the graph actually tries to tell you, right? So from t is equals to 3.0 is actually at this particular point up until this particular point. So I've been asked to define, or rather to state, what exactly is happening to the movement of the object. So let's just analyze this and find the value of x, right? So if we're at this point, the value of x is actually 0.8 newtons, right? If you look at this, 0.1, 2, 3, 4, 5, 6, 7, 8. So it's actually 0.8 newtons, right? So you have 0.8 newtons moving forward and you have 0.8 newtons moving backwards, right? So the value of x has actually changed. Now in this question, the value of x is actually 0.80 newtons. And that's very surprising, because if you look at this, the forward force and the backward force are actually equal. What does this mean? It means our object is in equilibrium because the forces are equal. Whenever the force that is going forward is equal to the force that is moving backwards, the object will travel at what we call a constant velocity. It won't accelerate, it won't decelerate. It will just travel at that force that it's moving at, right? An object will remain in a state of rest or uniform motion unless acted upon by an external force. Because this object was already in motion and there's no external force acting on it, because the forward force is equivalent to the resistive force, the object will keep on moving at its constant velocity. So they just want you to describe and explain. How do you know, right, what is happening? So you just need to state what exactly it is that you're seeing, right, and then explain why that is true, right? So the object is moving, the resultant force is 0, right? Because the force x and the resistive forces are equal, right? Hence, there is no acceleration, right? So this is just some extra information. Hence, there is no acceleration, right? But that's very important, because if there is no acceleration, the object therefore, right? The object therefore moves at a constant what? Velocity, right? So very important for you to remember those ideas. If the resultant force is 0, the object has no acceleration. So look at the resultant force, right? If you're just able to connect those two graphs, you'd realize that my object is moving at a constant velocity, meaning that there is no resultant force and the acceleration is 0. Right. So force X produces a total power of 2.0 watts. When moving from the moving the block between t is equal to 3.0 and t is equal to 6.0. Right. So we'll be asked to calculate the distance moved by the block during this time interval. Right. So we want to find the distance that the block has moved by, but we've been given only power, and we've been given the time as well, right? So how do we do this? Well, we know that power is actually force times velocity, right? So power is equivalent to force times velocity. But why is this true? Well, I've already explained it in some of my other videos, but I'm going to explain it again so that you can be able to understand this concept as to why power is equals to force times velocity, right? So we know that power is actually equals to the work done, right, per unit time. What work are you doing? How long did it take? That's your power, right? If you're doing work of 30 newtons, 30 joules, for example, sorry, in a time frame of 2 seconds, right? So it's 30 over 2, that's 15 watts, that's your power. But work done is actually force times displacement that is being moved. If you move a certain distance by applying a certain force, that's your work done, right? And time is that, right? But distance over time, that's actually equivalent to velocity. Displacement over time is actually equivalent to velocity. So power will be force times velocity. So that will be the value of your power. And if we were to go back here, we know that power is equals to force times velocity. What is our power? Well, our power is actually 2.0, right? This is equivalent to our force. But what is this force? Well, this force is generally the resistive force, right? So what power are we doing? We're doing work by overcoming the resistive force. Since the object is moving at a constant velocity, it means that the force is not actually changing the kinetic energy of the object. The only power that we're doing is actually by overcoming the resistive forces. So the force that we're overcoming is actually 0.80 newtons multiplied by v, right? So the value of our velocity will actually be 2.0 over 0.80. That gives us a velocity of 2.5 meters per second, right? So that's the value of our velocity. But if you have velocity and you have time, how do you find distance, right? So remember, distance is therefore equivalent to, right, speed times time, right? What is our speed? 2.5, right? So distance is actually equivalent to our speed, right, times our time. What is our time? Which is 3. That gives us a total of 7.5. Okay, so what are they looking for, right? So that gives us a total of 7.5, right? So what are they looking for? Well, they're looking for this formula, right? Do you know the formula that power is actually force times velocity? You can also give the other alternative. Power is actually work done per unit time, and those two mark you correct, right? And the other thing that they're looking for is the velocity. Can you calculate the velocity? If you do the other method, you can just find the work done and then find the distance that has been applied by that force. But if you're doing this method, the velocity will be actually that, and you know that the distance will actually be equivalent to the velocity times time. And if you do that computation correctly, you get an accurate answer of 7.5. So basically, that is how the marks are allocated, so you can be able to understand and how to calculate the distance that has been moved. Okay, move on to the last question for the dynamic section. So we've been given a block that is at rest at time t is equals to 0. So we know that the block is actually at rest when the time t is actually 0.0. And you've been asked to sketch a graph to show the variation of the momentum of the block with t is equals to from t is equals to 0 to t is equals to t is equals to 6.0. Right? So they don't really require values of the momentum. Again, this question has come. You need to understand how to sketch these graphs, right? A lot of people get stuck on understanding the shape of the graph and understanding what they actually need to do. So ask yourself, what do I know? Well, I know that momentum, I know that force, okay? So let's start. I know that force is actually equals to the rate of change of momentum, right? Therefore, if I have a momentum time graph, so if I have a momentum, which is equals to force times time, right? So that's basically my change in momentum, meaning that if I were to imitate y is equals to mx plus c, and I assume that this is 0, that would mean that my force is actually my gradient of this graph, right? So my force is actually the gradient of this graph. So if I have a force, but what is this force? It's actually the resultant force. The resultant force is actually the gradient of a momentum time graph. So whenever you're doing these graphs, right, ask yourself, what do I know about the area? Area doesn't really tell us much because momentum times time doesn't really represent a certain quantity that we can measure. But if you're looking at the gradient of a momentum time graph, that's actually force, right? Because force is actually the rate of change. Gradient, rate is actually related terms, right? So the gradient is actually the rate of change of something. So in order for you to get the gradient, you need to go back and ask yourself, what was my force? And was that force constant? So if you were to go back here, from 3 is equal to 0, right? Remember we said that we have 1.4 that is acting forward, right? So we say that we have 1.4 acting in that forward direction, right? So the resultant force was actually 1.40, right? Subtract 0.80. So that was basically our resultant force, right? Which is about 60 newtons, right? So with the resultant force of that, but did it change from 0 to 3? It didn't change. That remained constant. Right? So I just need you to understand that that value remained constant, but it was there, right? But only at a constant value. Meaning that if I'm to go here, I'm supposed to draw a gradient, right? That is constant. So if I'm to draw my graph, right, up until 3.0, which is here, right? So I can mark this point, right? Set a point here, right? I just need to draw a straight line that passes through the origin. Okay, so let me improve that. I just need to draw a straight line that passes through that origin, right? So basically, this shows that you know that the force is constant at one particular value. It's not changing. It's only remaining at one particular value, and that value is 0.60. They don't need us to tell them the numerical value of the momentum itself. But if I were to tell them, I'll just have to calculate that momentum and plot that point here. I'll just need to give a certain value and scale my graph, right? So remember this, the resultant force is actually the gradient of a momentum time graph, right? But what's happening after 3.0? Let's go back to our question. After 3.0, the resultant force is 0 itself, right? So if this is moving by 0.80 newtons, the resultant force is actually 0 after that particular period of time. So if we were to go back to our question, when the resultant force is 0, that tells me that the gradient is 0, right? So for resultant force to be 0, right, the gradient, right, has to be 0. So the gradient of a momentum time graph is actually communicating to me that the value of a certain force, right, the resultant force, exactly represents the gradient of that graph itself, right? So after a certain period of time, from 3 to 6, it's going to remain constant throughout its motion, right? So it's now going to be at a constant value. You get your 2 marks. So the first mark, they want an upward sloping line, right? So if they see this line that is upward sloping, you get your mark. Then if they see that other line, which is actually a horizontal line, right, at a non-zero value of your momentum, there is no step change in that momentum itself, you'll be able to get your other mark, right? So they just want you to know if, they just want to test if you know what exactly a momentum time graph tells us. It tells us the rate of change of momentum. I can get the force, which is the gradient from that graph, okay? Move on to the next question. This is a question on Hooke's law, right? So this is a question on Hooke's law, right? So let's get started. So a spring is suspended from a fixed point at one end, right? The string is then extended by a vertical force that is applied to the other end. The variation of the applied force with the length L is shown below. And you've been asked to state the name of the law that gives the relationship between the force and the extension. So this is really funny because the topic is actually surrounding Hooke's law, basically deformation of solids, and they just wanted us to state the law itself, right? So the law would be Hooke's law, right? So they just want to see if you know the law itself before you even start the question. So they just want to get your mentality into understanding what Hooke's law actually is. The next question, we've been asked to determine the spring constant in Newton per meter, right? What is the spring constant, right? Well, the spring constant is a unique property of a certain spring. Generally measures how hard it is to extend a certain spring, and it generally measures how difficult certain springs can be compressed or how difficult certain springs can be extended over other springs. But basically, force is equivalent to kx, right? From Hooke's law, we know that force is directly proportional to extension, right? So from Hooke's law, the force applied is directly proportional to the extension, meaning that your force will be equivalent to kx, right? So basically, this is what we call, in a nutshell, Hooke's law, right? So if we were to come back here, they just want us to find the value of k, right? So the value of k will actually be equivalent to my value of my force, right, divided by my extension x. So I need to ask myself, what is my force? And then to ask myself, what is my extension? But remember, I said, whenever you see a graph, it's a very high order question. Ask yourself, what do the x's tell me? So whenever you see a graph, ask yourself, what are the x's telling me, right? Also ask yourself, what is the gradient telling me? Also ask yourself, what is the area under the graph telling you, right? So basically, if you ask yourself those three things, graphs will be much easier to interpret, right? X's, gradient, and area under the graph. So whenever I see a graph, I ask myself these three things. What is my x's telling me? Is it momentum time? Is it force length? Is it force extension? Because in this case, it's actually force length, not force extension, right? So that's completely different, right? What is my gradient trying to tell me? Well, the gradient usually tells me the spring constant. Or what is my area under the graph trying to tell me? Usually tells me elastic potential energy. So if you keep on asking yourself these questions, you won't find the graph questions difficult to understand, right? So let's find a certain force that we want to find. So if we're looking from 0, right, from this point up until that point, right, we've applied a force of 12 newtons, right? So we have a spring that we've extended here, right? So we've applied that force that is actually of 12 newtons, right? And the spring is actually extended more than before, okay? So before, it had a length of 8, right? So here, there's a length of 8 centimeters, but now it has a length of, okay, so it's from here to here, it has a length of 24 centimeters, right? So before, the length was 8 centimeters. Now the length is actually 24 centimeters. So don't just read the graph and say, that's my extension. Well, it's not your extension, because it's just telling you the new length after we've applied the force of 12. The new length is now 24 centimeters, right? So the extension would therefore be 24 subtract 8. But remember, this is just something that you should know, that whenever it's in centimeters, always convert it to meters, so that it's very much easier for you to work with that. So it's actually 12.0 newtons divided by your extension, which is 0.240, subtract 0.08. Okay, so that gives you a value of K to be 75 Newton meters, right? So 75 and to the power -1. So K represents the gradient. So they just wanted to know if you know this formula. So if you didn't state that F is equals to Kx, or if you didn't state that K is equivalent to the gradient, you wouldn't get your mark, right? So if you were to find the gradient without even stating what it is that you're doing, you won't get your mark, right? Then the other mark would just be for the answer that you get, right? For all the calculations and for you getting that correct answer. Move on to the last question. On Hooke's law, we've been asked to determine the elastic potential energy when the force is actually 6.0 newtons. So how do you go on about this? Well, elastic potential energy, think of it as the amount of energy that has been stored when a spring has been stretched or compressed, right? So if a particular string and you stretch it, it stores energy in that spring itself. If you have a particular spring, you compress it, it stores energy due to its state of deformation, right? It stores a certain amount of energy. That is basically what elastic potential energy actually is. So they just want us to find that energy whenever we have a force of 6 newtons, right? So if you were to remember what I said in the beginning, the area underneath a force extension graph represents that elastic potential energy, right? So the area underneath this whole graph, right? So basically this area itself, right, basically represents elastic potential energy, right? But this is not a force extension graph. This is just a force length graph, but it's very important for you to keep in mind that this represents, right, the elastic potential energy, right? So for you to get from this point to that point, you've actually used 6 newtons, right? So for 6 newtons, you'll be somewhere here. So they want to find this area only, right? So let's just say A. They want you to find that area A, right? So it's a triangle. So basically, elastic potential energy, right, since it's a triangle, will be equivalent to half base times height, right, which is actually the force times the extension, right, which is force times the extension. But force is equals to kx, right? So EPE would actually be half kx squared, right? Where is this coming from? I know that EPE, right, is equivalent to half f of x, right? But f is equivalent to kx. So half of kx multiplied by x will give me half of kx squared, right? So this is where this is coming from. And what is your value of k? You just calculated from the previous question. So see how physics questions are connected. Whenever you get stuck to a question, always ask yourself, what have they given me before? That might actually help you to solve the question that follows, right? So we have this particular energy. We then say half of 75, which is 75. Okay, so half of 75 over here, 75 multiplied by your value of x, x squared, which is actually your extension from that particular point that you've reached, or you've gone from this point up until 16. So your actual change is actually 8, right? So it's actually 0.08 centimeters squared, and that gives you a total answer of 0.24 joules, right? So 0.24. So what do they want? They want you to see, do you know this formula, right? And what answer do you get, right? So remember, always state the formula that they want, right? They can either take that formula or that formula. Whenever you're asked a question, if you know a formula by head, put it down on paper. Chances are you'll be marked for getting that formula correct. Moving on to the next question, it's a waves question, right? So this topic is on waves, okay? So let's get to it. So we've been given a progressive wave that travels through a medium. So a progressive wave is basically a wave that transfers energy from one point to another, okay? So we've been asked to compare the directions of line P and Q if the wave is a transverse, right? So basically, they just want us to compare. If it's a transverse, right, it propagates along a line Q and it vibrates along a line P. Okay, so if it's for a transverse wave, as you can see on the right hand side of the screen, for a transverse wave, P and Q are actually perpendicular, right? So they are perpendicular. Perpendicular meaning that they form 90 degrees, right? So they are perpendicular, okay? But for a longitudinal wave, they're actually parallel, right? So they are parallel, right? Okay. A tube is closed at one end and the loudspeaker is placed near the other end, right? The loudspeaker emits a frequency of 1.7 kilohertz and the speed of sound is 340. A stationary wave is formed with an antinode A at the open end. There's only one other antinode, A, inside the tube. Determine the wavelength of sound. So it's very important for you to understand what exactly is an antinode, right? So an antinode is basically an area of maximum displacement. So this loudspeaker is actually causing a displacement at this point, right? So at this point, we have maximum displacement, and at that point, we also have maximum displacement. So basically, we have two antinodes, right? One antinode there and the other antinode there, right? So how do we draw a stationary wave? Well, an antinode means that I have an area of maximum displacement basically at this point, right? So let's first start with this question so that it's much easier before we get to calculate the length L of the tube. Okay, so the wavelength, we know that V is equals to F lambda, right? So your value of V is actually 340, that equivalent to your frequency, which is 1.7, right? Kilo basically means times 10 to the power of 3, times 10 to the power of 3 hertz. And these are just prefixes, right? As you can see on the right-hand side of the screen, I put some of the most common prefixes that you encounter. So it's very important for you to just know some of these prefixes so that you can be able to answer questions as they come. Okay, so our lambda will basically be here. Okay, so we then want to find the value of that lambda. So lambda will be equivalent to 340 divided by 1.7 times 10 to the power of 3. That gives us a lambda of 0.2, right? So 0.2 is actually the wavelength of our wave. The next question, we've asked to find the length of the tube. Okay, so whenever you see an antinode, there's a node that is immediately formed after that antinode, right? So since we had an antinode at the beginning, a node has to be formed. An antinode, a node has to be formed. How do I know this? Well, think of this way, right? An antinode is an area of maximum displacement. So if I'm to draw a stationary wave, I'm supposed to have a maximum displacement here, then a minimum displacement here, then a maximum displacement here, right? So something like that. Okay, so something like that, right? So this is a node, right? And that again is a node. So a node is basically an area of minimum vibration, right? So what is a stationary wave? Well, a stationary wave is basically when I have an incident wave and a reflected wave that superpose, right? So they meet at a common point, and the resulting displacement, right? They can either have constructive, where they build each other up, right? So we have the maximum displacement, and that is basically at this antinode here, right? So at the antinode, that is basically where you have the maximum displacement, right? So at this point, as well as at that point, right? So at these two particular points, that is where you have the maximum displacement. And at the nodes, you have minimum displacement. The waves meet, they crush each other up, and there's no vibration that is present at those two nodes, right? So whenever you have an antinode, immediately a node follows, right? An antinode, a node follows, right? And whenever you have a tube, if the tube is open at both ends, right? Very important for you to know this. If a tube is open at both ends, let's say it's like that, at an open end always, there will be an antinode that will be formed, right? So an antinode will be formed there, and an antinode will be formed there. If a tube is closed on one end, a node will always be formed at that closed end. So a node will be formed there, an antinode will be formed at an open end, right? So an antinode is always formed at an open end, and node is always formed at a closed end. So that's how I knew that at this point here, there's going to be a node, and at that point, there's going to be a node, and at that point, there's going to be an antinode, right? But very important thing to know is that whenever you have an antinode and an antinode that are adjacent to each other, this is actually half lambda, right? So the wavelength is actually the distance between an antinode, right? You skip an antinode, you go to the other antinode, right? So if you have two antinodes, one antinode here, right, and antinode number 2, they're basically half lambda, right? But you have one antinode, you skip an antinode, you go to another antinode that is basically 2 lambda, right? So that is basically lambda, sorry. So if an antinode to an antinode is half lambda, an antinode to a node is actually 1/4 lambda, right? So it's very important for you to know that whenever we have a node, right? So a node to a node is actually half lambda. If you have a node to an antinode, that's actually 1/4 lambda. If you have an antinode to an antinode, that's actually half lambda. If you have a node, and another node, right? So that is basically lambda, right? So basically that is something that you must keep in mind. So here, if we add these two up, we actually have 3/4 of lambda, and that is actually equivalent to our length, right? Our length L. But that's the length that we want to find. So L will be basically 3/4 times 0.20, and that gives us a total of 0.15, right? So that is the value of our length L. Okay, so again, in this question, they wanted us first and foremost to state this, right? So they just wanted to see if we know that V is equal to F lambda, right? And also know that lambda is equivalent to V over F, right? As we did over there. And they also wanted us to find our answer and get our wavelength correctly. In this one, it was just a matter of us knowing that 3/4 lambda is usually equivalent to our wavelength, and we'll just be able to get the 1 mark, right? Moving on to the next question, we've been asked to find the maximum wavelength of sound, right, that can be formed, the maximum wavelength from the loudspeaker that can produce a stationary wave in the tube itself. Okay, so the important things that you need to know, especially when these questions deal with maximum amplitude itself, right? So we need to understand what exactly is amplitude and what exactly happens whenever we have a stationary wave, right? So if we look at a stationary wave, okay, so let's remove this. If we look at a stationary wave, generally the lowest wavelength the lowest frequency that we can ever get is due to the biggest wavelength that we can ever get, right? What do I mean by this? Well, the moment you keep on putting more antinodes and putting more nodes, it's like you're compressing your wave. Look at this, right? If I keep on putting a lot of nodes, right? If I keep on putting a lot of nodes, a lot of antinodes, I keep on compressing my wave, right? You can agree that there's so many nodes, right? You can agree that there's so many nodes. There's an antinode, an antinode, an antinode, an antinode, an antinode, but it's still the same length, meaning that my wave here actually is a very small wavelength, right? Because the wavelength here is actually from this node, antinode here, to that antinode here. That's actually my lambda, right? What if I were to put more waves, right? So let's put more waves. If I were to put more waves and I keep on doing that, right? You'd realize that my value of lambda actually gets smaller, right? My wavelength keeps on getting smaller. So if this is my antinode, if that's my antinode and that is my antinode, right? So if that's my antinode and that again is my other antinode. This is actually my value of lambda, right? So you can see that the value of lambda gets smaller and smaller the more you compress a lot of wavelength in a very tight space, right? But we know that, right? We know that wavelength is actually related to the frequency itself, right? We know that frequency, okay, v is equals to f lambda. If v remains constant, we know that the frequency is actually inversely proportional to 1, directly proportional rather, to 1 over the wavelength, right? So what does this mean? If you were to increase your wavelength, right? If you were to increase this, it means that this decreases, right? So if you were to decrease this, it actually means that this, right, increases, right? So that's basically the basic relationship between frequency and wavelength that I want you to know. So as we keep on compressing a lot of waves in one tiny area, the frequency keeps on getting higher. So the first frequency that you get, which is the fundamental node, you keep on getting what we call overtones, right? As you keep on having more and more waves compressed, the frequency gets higher, but at a cost, the wavelength gets shorter. So how do you find the maximum wavelength? Well, the maximum wavelength is when you have the greatest number of waves, right? Sorry, the maximum wavelength is when you have the least number of waves or the least number of antinodes and nodes that you can compress in one area. So how do we get that? Well, we get that if we just have, remember if we go back to the fundamentals, right? I say that whenever you have an open end, that's an antinode, a closed end, that's a node. So the most simplest one that you can ever form is actually something like that, right? It just says one antinode over here and one node over there, right? So this is basically just the wave that you have, right? We only have that. And remember, like I've said, if you compare it with the other waves that I drew, this is an antinode over here, and this is a node over here. This is actually 1/4, right, of a wavelength. This is not even a wavelength itself. It's 1/4 of that wavelength. But as I was putting more antinodes in the previous things that I once did, you would appreciate that I was actually seeing lambda on that graph itself, and it kept on getting smaller. But here I can't even see the wavelength itself. I'm only seeing 1/4 of the wavelength, right? So that is the maximum wavelength that I can have. That is what I call the fundamental mode. I can't have any other wavelength that is smaller than this. I can't fit any other wavelength that isn't 1/4 of a lambda, right? So this is my maximum wavelength that I can ever have. And we know that if this keeps on getting smaller, right, since this has decreased, right? So this has decreased to when it's only 1/4 of lambda. What does this tell me about the frequency? This is when I have the minimum frequency, okay? Because this is the maximum frequency that I can have, mean that gives me the minimum frequency that I can ever need. That is what we call the first fundamental mode, right? So by keep on putting more waves inwards, I keep on causing the wavelength to get smaller, but here it's only 1/4 lambda. But remember, 1/4 lambda is actually equivalent to L. So if I'm going to go here, 1/4 lambda, right? So 1/4 of lambda is actually equivalent to L. So what maximum wavelength do I need so that the speaker can actually produce a stationary wave, right? So the maximum wavelength from the speaker that can then produce that stationary wave would therefore be, okay, so since our length here is actually 0.15, as I've calculated there, lambda will actually be equivalent to 4 times length, which is 4 times 0.15. That gives me the value of lambda, which is 0.60, right? So that is my maximum wavelength that can produce a stationary wave in the tube. So I want you to understand this, guys, right? Whenever you see the word maximum, always think that is the fundamental frequency mode. Whenever the frequency is the lowest, that is where I have the maximum wavelength. Given the situation that you have, try to analyze, can I fit any wave, right? Can the wave get bigger than what it already is? Never, right? But the more I keep on putting more nodes and more antinodes, the smaller the wavelength becomes. So the maximum wavelength that I can have is 1/4 lambda, and the lambda will therefore be equivalent to 0.60 meters, okay? Moving on to question number C. We've been given two polarizing filters that has been arranged. So this is Malus's law, a new addition to our syllabus. So I've posted already a video on Malus's law, but I will explain it again in this video, but I would highly recommend that you watch my video. As you can see on my card above, it's a video where I was explaining how Malus's law works, as well as other questions that I posted on Malus's law. So I highly recommend that you watch that. That would be very helpful for you to understand, right? So if you watch that video, you come back and you're able to even answer this question on your own, right? So we've been given two polarizing filters that has been arranged so that their planes are vertical and parallel, right? So the first filter has a transmission axis at an angle of 35 degrees, okay? And angle alpha is actually greater than 35 degrees and less than 90 degrees, okay? So very important for you to know that. And we've been asked to show that the intensity of light transmitted by the first filter is actually 5.7, right? So Etienne Malus came up with Malus's law that relates the intensity that is incident and the intensity that is transmitted, that goes out, right? And he came up with Malus's law. We said that the intensity that you get out is actually I naught, right, cos squared of theta, the intensity that you put in, okay? So if we look at this, we have incident light beam that is vertically polarized, right? So the light is coming in like that, right? So it's coming in vertically polarized, and the angle is actually 35, right? So with Malus's law, you need three things, right? I always say you need a polarizer, you need an analyzer, and you need a transmission axis. If you understand these three things, you've understood Malus's law. So you need to ask yourself, what is my polarizer? Well, the initial polarizer, we don't know it because it's already coming in vertically polarized, right? So it's much easier to answer the question. And my analyzer for the first one is actually this one, right? So I'm basically considering this as my initial analyzer, okay? So what is my transmission axis? This is this one, which is for this slide that is coming in. So my angle will actually be these two angles that I'm comparing. So this will be my angle theta, okay? So if we were to go here, the angle theta is 35. It's coming with an initial of 8.5. So that would be 8.5 cos, right, of 35, right? So all of that squared, right? So how do you punch cos 35 squared on your calculator? Cos squared theta is actually cos 35 of that, put that in brackets, and you square that, right? So that gives you an answer of 5.7 watts m, right? Approximately to two significant figures, because the least value that we have is 8.5, that is 2SF, so our answer must also have two significant figures. So we have shown that that is equivalent to that, right? Moving on to the next question, we've been asked to, we've been given the intensity of light transmitted by the second filter. And the question requires us to calculate the angle alpha, okay? So this is the angle that the question wants us to calculate, right? But we've been given the intensity of light that is produced outside of that filter. What can we do with this? Well, we can find the value of theta, right? Let's just find the value of theta. But remember that this light is now coming into this filter already polarized, right? So it's already having its vibrations restricted to move in a certain angle, okay? So what is that angle, right? So let's just look at that angle, right? So we know that, again, the intensity will be equivalent to, okay? So intensity will be equivalent to I naught, right, cos squared of theta. So the intensity that we are getting out is actually 5.2. Intensity that we put in, 5.7, right, cos theta squared, right? So cos theta is actually equivalent to 5.2 divided by 5.7, the square root of that, right? So theta is actually a cos the square root of 5.2 divided by 5.7. And that gives you an answer of theta, which is 17.3 degrees, right? But is this the angle alpha? Well, it's not really the angle alpha, because think about this, right? Light is already coming in at 35. And this question is saying that the angle between this, right? So we already have this axis that we have here. The question is already saying that the angle between a smaller axis, that this angle is coming in, right? And that one is actually 17.3 degrees. It's not really the big angle, whole angle alpha, because whole angle alpha is actually measuring this light here, right? Because it's vertical and that angle alpha, right? So, but here we've already rotated our light at 35 degrees. By the time it comes into that second one, it's going to be rotated down further by 17. So the angle will actually be 17.3, but the total angle of alpha will actually be 35 plus 17, right? So alpha will actually be 35 plus 17.3. That gives you a total of 52 degrees to 2 SF, right? So the first thing that they need to know is, do you know this particular aspect, right? So if you're able to get this value of theta, you just get your first mark, right? But the second mark, the answer that they want would therefore has to be that one, right? Remember, the angle alpha, always ask yourself, what is my transmission axis? Your transmission axis, well, is actually this value itself, right? Your transmission axis, you're actually looking at a certain value that is 70.3 between the light that is coming in and the light that comes out. But that is not your value of alpha as a whole, right? So always keep that in mind. And if you were to even look, right, this angle is actually bigger, right? Look at this. This is actually a bigger angle, right, than that angle itself. They just want to know, right, what is the new one, how big it is by 17.3. And if you add the previous one of 35, 52 becomes the whole angle alpha, okay? Moving on to electricity. We're almost done. We're only left with 2 questions, right? So this is the topic of electricity. Okay, so let's get to it. The current in a filament lamp decreases, right? So we have a filament lamp and its current decreases, and we've been asked to state and explain how the resistance of the lamp changes. Okay, so basically a filament lamp, how it works is it's almost this particular graph, right? So this would be a current against voltage graph for a filament lamp, right? So this is for a filament lamp, right? So the question is asked us to state how the resistance of the lamp actually changes, right? So they want 2 things. They want us to state and explain how the resistance of the lamp changes. So what is resistance? Well, resistance generally is the ratio of voltage against current, right? So resistance, right, is actually the ratio of voltage and current, right? So it's usually this particular ratio. But this graph gives me the variation of current against voltage, right? So it's the opposite of this, right? So this graph actually gives me delta I. So the gradient of this graph actually gives me delta I over delta V. But don't think much about gradient and resistance, right? This doesn't really mean that resistance is the gradient of this graph. I want you to think of this in terms of ratios, right? I want you to think of what do these ratios mean? Because that will get so much easier for you to understand what the resistance actually mean, right? So if we were to look at this, right? So let's just look at this ratio, the ratio of current against voltage, right? So as you can see that the line is sort of starting horizontal, but it starts to sort of have a gradient that is decreasing, right? So if we were to draw a line here, right, versus us drawing a line here, versus us drawing a line here, right, you can see that the gradient is actually decreasing, meaning that this ratio of delta I over delta V actually decreases, right? For example, it might be 2, right? For example, maybe it would then be, if it decreases, it might be 1, maybe it might be 0.5, right? But what does this mean about the resistance itself, right? If delta I over V decreases, delta V over I, which is actually 1 over delta I over delta V, will actually increase, right? Because you're saying maybe 1 over 2, right? That's actually half. Maybe 1 over 1, that's actually 1, right? So you see that your answers keeps on getting bigger and bigger. 1 over 0.5, that's actually 2. So your resistance increases as the graph actually decreases. So that's the very most important thing that you need to understand, right? So for a filament lamp, the resistance actually, right? So the resistance actually increases, right? Right? But we just need to state and explain, right, how exactly happens to the resistance of the lamp itself, right? So, okay, okay. So the question said that the current actually decreases, right? So the current actually decreases, right? Okay, so we were going in reverse, right? So if the current is decreasing, it means that we're actually going down the axis itself, right? So if current decreases, it means that the gradient itself is actually increasing as we're going through this particular value itself, right? So if the gradient is actually increasing, if you do it in the opposite way, it usually means that the resistance will also decrease, because the ratio of that is actually increasing, right? So if this ratio increases, it actually means that this ratio will actually decrease, right? But it's still important for you to understand the opposite. If current increases, right? So if we're looking in the opposite direction, if current is actually increasing, the ratio of this one actually increases, actually decreases as you go up, and then the resistance actually will begin to increase. But if you're having your current decreasing, your ratio of delta I over V will actually begin to increase, but your resistance will begin to decrease, right? So in this question, if the current is decreasing, the resistance actually decreases, and this is actually because the temperature, right? Because the temperature actually decreases, right? So basically that's the reason why the resistance actually decreases, right? Okay, but why is it that temperature decreases, the resistance actually decreases? Well, if you were to think about this, the current in a filament lamp, right? If you have seen a filament bulb, they have what we call a filament wire, right? If temperature increases, the vibration of atoms inside that wire actually begins to increase, right? Meaning that the electrons, as they're moving, encounter much more resistance if temperature is higher. But the reason why the temperature, if it's decreasing, the vibration is less, the resistance will actually also decrease, meaning that the electrons will face less resistance as they're moving, because the vibration of the atoms is actually way, way, way less. Okay. Moving on to question B, we've been given a cylindrical wire that is length L and resistance R, and we're given the total number of free electrons contained in the volume of a wire, that will be N, and each free electron has a certain charge, right? So we've been asked to determine expressions in terms of some or all of the symbols for the current in the wire. Okay, so basically current is actually velocity over ratio, right? So current is actually the voltage, divided by the resistance, right? So current is actually the voltage divided by the resistance, right? So we have the potential difference over there and the resistance, which is R, right? So the value of current will usually be V over R. And it wants to find the average drift velocity, the average drift speed of the free electrons, right? Again, we know that current is actually V over R, right? But how do we find the average drift velocity in terms of those things that we know, right? So if we were to go back to our data booklet, right, that they give us at the beginning, they've given us the equation I is equals to NAVQ, right? So this equation for electric current that relates the area, right? So in this equation, the A represents the area, right? And the N represents the number density, right? How many electrons are present in a unit volume of itself, right? And V represents the drift velocity, right? And Q, right? So this value of Q actually represents the elementary charge, right? So it represents the elementary charge, which is 1.6 times 10 to the power of negative 19, right? So it's actually this value itself, right? So this is what E actually represents, right? Which is also the value of Q. So this is basically an equation that you need to know that talks of the drift velocity, right? So the drift velocity is actually how fast the electrons are moving themselves, right? So based on that equation, we know that I is equals to ANVQ, right? But N is actually the number of electrons per unit volume, right? So we know that I is equals to V over R, as we've previously stated, right? Our area remains the same, but our number density is actually the number of electrons per unit volume, but volume is actually equivalent to area times length, right? Times your value of your drift velocity V times the value of E, right? So those cancel out. So we're left with V is equivalent to R times N times the small letter v times E. Okay, so basically this is the value of that we want, right? So this L goes to the other side. So VL, right? So this multiplies that. So VL is actually equivalent to this whole expression itself. Okay, so the value of this value of V, right? So the drift velocity, which is actually V, will be equivalent to the volume, right? So sorry, the potential difference, the big V, multiplied by the length L, right? Divided by the number density N and R and E. Okay, So basically, average drift velocity will be potential difference times L divided by N times R times E. So this will be the formula for the average drift velocity. Okay. So very important for you to come up with that particular formula. Okay. And the next one, we've been asked to find the average time taken for an electron to move along the full length of the wire, right? So time is actually, okay, distance over speed, right? So time, right, is actually the distance that has been moved, okay, divided by the speed itself, right? So what is our distance? It's actually L, right? And our speed, as we've calculated, is actually VL divided by RNE, right? So time will basically be equivalent to RNE divided by V, right? So the time taken will be RNE divided by V. Okay, moving on to question number 7. Okay, we've been given a battery of EMF 9 volts and negligible internal resistance that is connected to an LDR, okay, as well as a fixed resistor. And we've been asked to calculate the potential difference across the LDR. Okay, so how do we do this, right? Okay, so the question has asked us to calculate the potential difference across the LDR. So using the potential divider formula, we actually say that 1,800, right, divided by, right, so these are going to share the potential difference based on their resistances, right? So it's going to be divided by 1,800 plus 1,200 multiplied by 9, right? So this gives us a total of 5.4 volts, right? So what are they looking for, right? They're looking for this particular formula itself, right, that shows that you know how this is calculated, and they're also looking for the final answer itself, right? So basically, electrons, as they come, as they're given EMF, they're given energy, they distribute that energy based on the resistances of the products or the things that are receiving that energy itself, right? So they share their the energy based on the values of the potential difference, right? So if that energy is bigger, right, so if it has a greater resistance, it gets a greater amount of energy. Smaller resistance gets a lesser amount of energy, right? So basically, if it has 1,800, it should get the greater portion of 5.4 volts. If it has 1,200, it must get also a lesser amount of that energy, okay? So basically, that whole circuit has now been transformed sort of into a potentiometer, right? So this is basically more of a potentiometer question, and also going to be explaining the whole concept of potentiometers itself, okay? The important thing that you must think about is what it means when they say the galvanometer reading is 0, okay? So whenever the galvanometer reading is 0, it means that no current flows through, right? We know that this is a loop, right? So we have two loops. This is a loop on its own, okay? And this whole outer thing is actually a loop on its own, right? So you have two loops, one loop which is the bigger loop and the inner one which is a small loop, right? So electrons are going to reach this junction and they have a decision to make, right? They can go in this route or they can go in that route. So in order to share the work, they divide, they branch, others go down and the others go to the side, right? But they have the same amount of energy. They just, to make the work easier, these two resistors want to benefit and the wire also wants to benefit, right? Everyone really wants the energy. So electrons divide themselves, right? Others go down and others go to the side, right? So basically the current actually decreases because the electrons are actually separating, but the energy that they possess doesn't change. Meaning that XY, right? So from this point to that point actually gets 9 volts, right? And from this point to that point actually also gets 9 volts, right? But you'd see that no current is flowing from this point, right? Let's just give it a fake name and just say maybe point Z, right? So no current is flowing from point, oh sorry, there's already another thing named Z, or let's say W. So there's no current flowing from W to Z. Why? Because the potential difference is the same. Current will not flow, or electrons will not flow to a region where they already know that the potential difference is already okay, right? So the potential difference is the same. These electrons that have moved here have already given an amount of energy, right? So they've already given 5.6 volts across this. That is also the same across this one, which is also 5.6, right? So no current flows through from W to Z because XY actually has 5.6 volts. And electrons at this point of Z, right, and electrons at that point also have 5.6. So there's no need for electrons at W to help electrons at Z, right? Because electrons at Z might need help to help with the remaining electrons that would be needed, right? So if electrons arrive at point W, they have a decision to make again. Can they go to Z or should they continue with their route, right? They won't go to Z because the potential difference is the same. Z doesn't need help at all. So they'll continue moving across there, then they will finish their journey, right? So XY gets 5.6 and that point to that point also gets 5.6. So how do you calculate length XY? Well, length XZ, right, against the total length of the wire, which is actually 1.2. Okay, we've been told that the length is 1.2, which is actually 1.2, right, must be equivalent to 5.4. Okay, so xz will actually be equivalent to 9. Okay, so y will actually be equivalent to 5.4 times 1.2 divided by 9. So the value of xz will actually be equivalent to 0.72, right? So 0.72 meters, 0.72. Okay, so the environmental conditions change, causing a decrease in the resistance of the LDR. The temperature, however, remains constant, and it wants to state whether there is a decrease, an increase, or no change to the intensity of the light illuminated by the LDR. So I basically want you to understand what an LDR is and how an LDR works, right? So an LDR basically operates on changes in the environment, right? Light intensity. If light intensity changes, the LDR will also change, right? So basically they obey this graph, right? So LDRs basically, so it's a graph like that, okay, and that. So if this is dark, right? So if this is dark, we also have high resistance, and if this is bright, we have low resistance, right? So the brighter it gets, the lesser the resistance that you have, right? So this actually represents resistance, right? But the darker it is, the more the resistance that you have, right? The brighter it becomes, the lesser the resistance. The darker it is, the more the resistance. So basically that's how an LDR works, right? If it's brighter, right, we have very low resistance, and you can actually apply that in different problems, right? But there are many kinds of LDRs, and not all of them have this graph. But basically for AS, this is an important graph that you need to know. So if the decrease in the current is present, what does it tell me about the intensity of the light? Does it increase? Does it decrease? Or does it have no change? Well, basically, if the resistance decreases, basically it means that the light intensity has actually increased, right? So if light intensity increases, if it becomes brighter, resistance decreases, as you can see from this graph. So basically, the intensity of the light here will actually decrease. So the intensity actually decreases, right? The total power produced by the battery itself, okay? So if the LDR here decreases, right? So let's look at this question. So if the LDR decreases, right? So the resistance of here was once 1,200. Let's assume that it's now 1,000, right? Let's just say it's now 1,000. Okay, so this becomes 1,000 ohms. So we want to find so let's assume that this decreases to 1,000 ohms, right? So we want to find the effect that this will have on the total power produced by the battery itself. Okay, we know that power, right? Power is actually equivalent to I squared R, or power is equals to voltage times I, or power is equals to V squared over R, right? So basically these are some of the formulas that we know surrounding power. They just come from knowing that power is equals to work done per unit time. Work done is actually voltage times Q, and Q is equals to IT. So power is equals to VI, right? And if you manipulate that, you get I squared R or V squared over R. Okay, so what happens to the total power produced by the battery itself, right? So I have resistance. What else isn't changing? It's EMF, right? So I can look at this equation. If I take that equation out, I have P is equals to V squared divided by R, right? But this is remaining constant, right? So this remains constant, right? But what is happening? This R is actually decreasing, right? Because the total resistance of my system is decreasing. And if from this ratio, if R decreases, the total power produced actually increases, right? So the total power produced here actually increases. So I want you to think about this, right? Whenever you're given these equations, especially whenever they talk of power, think of what equation can you actually use, right? The length xz, so that the galvanometer actually reads 0. So the length xz is actually this portion itself, right? So if this 1800 now is actually smaller, right? Now it is a very small resistance, right, that we're talking about. What will happen to the length xz so that the galvanometer actually reads 0? Okay, so the length xz has to decrease. What do I mean by this? Well, if this, let's say, is 1000, meaning that if electrons come here, they no longer need to give 5.4. Electrons are very strategic, right? They know that if something has bigger resistance, it needs a lot of energy. So when they arrive at this 1000, they realize, it has 1000 ohms, so let's just give it maybe 3.6, right? So they won't give it all that amount of energy. The rest they would give it to the 1200 because now it's bigger than the 1000 ohm resistor, right? Because the resistance of that has decreased. Meaning that xz, this distance actually has to decrease. Why does it have to decrease? Well, because for this to be equal, right, we have to be maybe somewhere here. That is where this has to be 3.6. So 3.6 and 3.6 are equal, and this will actually give me a value of galvanometer reading of 0. So right now it's not 0 because current here and there is not the same. If current arrives here, it's going to try and fill that gap here so that it can accompany and help that deficit over there. But if we push it over here to somewhere over there, it actually means that, okay, so if we were to look at this and actually move it over there, right, you see that that really affects how everything is going to operate. So the value for of xz is actually going to decrease. Okay, so the value of xz actually decreases. So that length, okay, so if we were to look at it, actually decreases, right? So very important. Moving on to the last question, it's particle physics. Okay, so we've been given nucleus P and nucleus Q, right? So nucleus Q is unstable and emits a beta minus particle to form nucleus R. For nucleus P and Q, compare the number of protons and the number of neutrons, right? So let's just write what we know, right? What is for P and Q? Compare the number of protons. Well, the number of protons are the same, right? Because they're basically isotopes, right? So the number of protons are the same, right? But the number of neutrons are actually different, right? They're actually different, or they're actually unequal. Okay. Next one. When nucleus Q decays to form nucleus R, the quark composition changes. State the change to the quark composition of the nucleon, right? So let's write that formula for beta minus decay. So if we have P, right? So we have which nucleus decay? Nucleus Q. So if we have nucleus Q, right, that is A and Z, and it undergoes to form nucleus R plus a beta minus particle, right? So this is beta, 0, -1, plus it releases an electron anti-neutrino, right? Something like that. But this is actually increasing by 1, right? But what happens during beta negative decay? Well, a neutron is actually turned into a proton, right? So basically, that is what happened. That is what happens during beta minus decay, right? So a neutron is turned into a proton, right? And it releases that beta particle and electron antineutrino in the process, right? And a neutron, we know that it's made up of an up quark, a down quark, and a down quark, right? So the change here is actually that a down quark will actually be converted into an up quark, right? So a down quark changes into an up quark so that we form a proton, right? And we release that beta negative particle, right? And an electron neutrino will be formed. So this is for beta negative, but if it's beta positive, right? So if it's beta positive decay, it's actually the opposite. A proton actually changes, so this is 0, okay? Because neutrons have no charge, so it should be 0 there, right? So in beta plus decay, a proton will actually now convert into a neutron, right? But it will now release an electron neutrino, a positron rather, and an electron neutrino, right? So it won't be an anti-neutrino, it will just be an electron neutrino, right? So, but basically during beta negative decay, the composition that occur is that a down quark, okay? So basically a down quark changes into an up quark, right? So it changes into an up quark, okay? So down quark changes into an up quark, okay? Right. State a name of another particle that must be emitted from nucleus Q in order to form that beta negative particle, and that particle has to be an electron anti-neutrino. Okay, so that's an electron anti-neutrino. Okay, so one other thing that I want you to remember, so sort of a shortcut that I use to understand what beta negative what is beta negative and what is beta plus decay. Okay, so if you look at the word beta negative, right, as well as the word beta positive, right, look at these two words, right? Beta negative starts with an N, right, this N. So I usually say that this N starts with a neutron, right? So beta negative starts with a neutron that has to turn into a proton. In order for that to happen, it then releases a beta negative, right? So here, it will then be a down quark that changes into an up quark, right? But for beta positive, this P represents first start with a proton, right? And that proton would turn into a neutron. And in a proton, you know that the most abundant thing is an up quark that would then turn into a down quark, right? So this is a very good mnemonic that will help you in understanding what happens. So whenever you hear the word negative, beta negative, just remember neutron, right? Start with an N, neutron turns into a proton. Beta positive, P stands for proton, turns into a neutron, right? So very important for you to just know that. A hadron consists of two charms and one bottom quark, right? So a charm actually has a charge of 2 over 3e, right, plus 2 over 3e, and one bottom quark, right, actually has a charge of negative 1 over 3e, right? So the total, if you have two charm quarks, it will therefore be plus 2 over 3e plus 2 over 3e minus 1 over 3e. That becomes a total of 1e, right? So the total will be plus 1 over plus 1e. That will be your charge, right? Again, how do you know that the charm is plus 2 over 3? Very confusing because charm and strange are very tricky, right? Remember, the top is actually plus 2 over 3, right? The top, so it has to be positive 2 over 3. Bottom, okay? The bottom just has to be negative 1 over 3e. If you have up, right, an up quark, up means at the top, again, plus 2 over 3e. Then if it's down, it's negative 1 over 3e. But for charm and strange, they're a bit tricky. So I usually use this example that if you have charm and you have strange, right? Strange is the only thing that is this letter N, right? So it's the only thing that is this letter N. And that N actually represents negative, right? So whenever you think of the word charm, there's no N, so it has to be plus 2 over 3e. The word strange has an N, so it has to be negative 1 over 3e. So those are some of the tricks that you can use to save your time. And instead of just, memorizing that charm is plus 2 over 3e, you actually have something that can help you during that process. So this was my video and I'm done. So thank you guys for watching and I hope you like the video. Please comment if you have any queries whatsoever so that I can be able to improve and be able to upload more better content, right? Thank you for watching. I'll see you in the next one.